Howdy, students. This is going to be a lesson over chapter 13, and we're not going to get to 17 in this one, but in the first video, we're going to cover what the equilibrium condition is. We're going to utilize the concept of equilibrium constant, and we're going to describe the equilibrium position of particles involved in a chemical reaction. And then we're going to use those pieces of information to calculate the equilibrium constant for aqueous and gaseous systems. So make sure you have a calculator, and you'll be pausing the video to work out some problems. Okay, the equilibrium condition. As we've learned in stoichiometry, we've assumed that chemical reactions proceed to completion. It's a forward reaction, and that all reactants are converted to products. At this point, we've seen this type of arrow. Many chemical reactions actually stop short of completion, and we are going to talk about what happens when we are able to go forwards and backwards. So what is equilibrium? Well, it's a state where concentrations of products and reactants remain constant over time. So there's a steady state where it reaches a point where we are not going forwards or backwards, and we are just staying steady. It can be dynamic, meaning it moves. Particles are constantly forming products and then reforming reactants. It's going back and forth, and we can shift these equilibrium values. If mostly products are formed, we say that the reaction lies to the right. So we might have a larger arrow. If mostly reactants are present, said to lie to the left, which means we might have a small forward arrow but a larger backwards arrow. So if we're looking at this picture here, the red line indicates that the forward rate, you'll see a negative slope. There's a consumption of the reaction. And the reverse rate would be the opposite. You'll see equilibrium lying towards the bottom, which means that we're favoring the forward rate. More of the forward rate is happening. Any chemical reaction in a closed vessel will eventually reach equilibrium. Now, if we open up a container, we're subjecting more molecules to become a part of our system. At equilibrium, the forward reaction rate will equal the reverse reaction rate. So we're going to take a moment and we're going to draw some pictures here explaining what's happening as particles eventually reach equilibrium. So you may want to pause after each section here. I want you to draw out all 6 of those molecules, and that's in O2. On the graph, you'll notice that we start out with 6 molecules of NO2 and 0 molecules of product. Well, what we know about NO2 is that it dimerizes. So here, 2 of the NO2 molecules have dimerized, and let's reflect that on the graph here. We now only have 4 molecules of NO2, and we have 1 molecule of N2O4, excuse me. Okay, more time passes, and again, another pair of NO2 molecules dimerize. And then in the third picture, you'll notice that there is no change in products. So we have the same. And what's going to happen is the concentration of the products and the reactants are constant, stays the same. Pause the video if you need to finish sketching in the graph. Not in your notes, but let's consider something. This is called the Fritz-Haber reaction, forming ammonia. What is the equation for this reaction? Well, we have 3 reactants. It's a synthesis of ammonium, so we're going to add diatomic nitrogen to diatomic hydrogen to form ammonium. How much of the product do we start with? Well, we don't have numbers, but what we can tell is at the beginning, we don't have any products. You'll see the NH3 is at 0. Which direction is favored at the beginning of the reaction? Well, if we're starting with 0 products and all of the reactants, the only way that it possibly can go is in the forward, or what we call the right direction. Why does H2 have a steeper curve than N2? Well, if we look at the stoichiometry, it's a 3-to-1 ratio. We use more moles of consumption of H2 than we do N2. At equilibrium, are the amounts of reactant and product the same? And if we look, no, these lines are at different concentrations, but you'll notice that they are constant. There's more hydrogen in ammonia than there is nitrogen. So, in this first section, 13.1, what are the points to take away? Molecules will react by colliding. So, if we increase the concentration, reactants lead to the formation of products. We learned that in the kinetics unit, the collision theory. When product concentrations increase, the reverse reaction is favored, and we're going to learn about Le Chatelier's principle later in this unit. All equilibrium systems are working to increase entropy, which we call delta S, and we will learn about that in chapter 17, while decreasing free energy, which is delta G. We'll learn about that later too in thermodynamics. The final system should have the lowest energy. A system is going to remain at equilibrium unless disturbed. And again, that is Le Chatelier's principle. We will learn more about that later. 13.2, we're going to talk about the equilibrium constant. And this is a capital K, not a lowercase k like rate. And we're going to look at the law of mass action. The equilibrium constant can be noted by several different terms. Capital K is normal. If you see a subscript C, that stands for the equilibrium constant. And then EQ would stand for equilibrium instead of C, constant. So let's take a general example here. A plus B yields C plus D. You'll notice that it is in equilibrium. We have coefficients J, K, L, and M. Here's the general form for an equilibrium reaction. What you'll notice is that we have products on top and reactants on bottom. Recall that brackets in chemistry indicate concentration or moles per liter. The exponents of each of the reactants and products are the coefficients of the reactant. In rate, the overall equation, we could not assign coefficients as exponents unless it was an elementary mechanism and it was the slow step. Let's look at how we can derive this equation from the rate law. So again, here's the general equation. What I know is that in this reaction, there is a reverse and a forward reaction. Each of those is going to have its own rate law. So if we write the rate law for the forward reaction, we would have K A to the power of J if this is the elementary slow step for a mechanism, B to the power of K, again, elementary slow step, and the rate itself is going to equal, and remember this is equivalent to the rate, that is going to equal the rate of the reverse reaction, which would be K C L D to the power of M. Because this is at a certain temperature, the rate constant K is going to be the same. When we divide over terms, the equilibrium constant is going to be C to the L, D to the M, divided by A to the J, B to the K. And that's what we see here for the equilibrium expression. Okay, so here's an example. Write the equilibrium expression for the following equation. K equals, we're going to do products over reactants. So KC or KEQ, I like to use EQ personally. Products are NO2 times H2O over NH3 reactants and O2. Now, the coefficients are the exponents here, so 4, 6, 4, and 7. And that is the equilibrium concentration. Equilibrium constant. Okay, so what if we know the concentrations? If we know the equilibrium, and this is key, they have to be equilibrium concentrations. We can calculate the equilibrium constant Kc. What we're going to find is that later, if we look at the initial rates, we get this letter Q. So let's be sure we're looking at equilibrium concentrations. We are only going to use gases and aqueous solutions in the equilibrium expression, and I can't stress that this is so important. So when we see gases or aqueous solutions, we will use those. We will not be using pure solids or pure liquids. So here's an example. Calcium carbonate is in equilibrium with calcium oxide and carbon dioxide. If we write the equilibrium expression, you'll notice that the solid compounds are not included and it's products over reactants. So we just have K equivalent to the concentration of CO2. If an equilibrium reaction is composed of reactants and products all in the same state, we call this a homogeneous solution or homogeneous system. If they are different, we call it a heterogeneous system. So if we are looking at how K changes, it's only going to change with a change in temperature. If we increase the concentration or the pressure, that will not affect the value of the equilibrium constant. So if we're looking at the flasks here, what we'll notice is we have an equilibrium situation on the far left flask. If we make an addition of N2 gas, what we'll find is that the ratio of the gases will eventually end up over a certain amount of time, T. They're going to end up in the same ratio. So concentration does not affect the value of K. Over time, equilibrium will be reestablished. The concentrations may be different, but the value itself will not change. We can actually easily manipulate the value of K if we change the stoichiometry of the reaction. So take the first example. A normal generalized equilibrium expression can be written according to the forward and backwards reaction. We can plug in equilibrium concentrations and actually solve for the value of KEQ. Now, once we have that, we can do a couple of different things to manipulate the values. So look at the second column here. So if we're looking at column 2, let's call it K prime because this has been reversed. Reactants and products are now flip-flopped. If the reaction itself is flipped, all we have to do is take the inverse of K. So 1 divided by K. We'll call it K prime. Now, what if we change the stoichiometry? What if we double all of the moles of reaction? What if we triple? Okay, let's call that K double prime. You'll notice that the exponents in each of the terms in the equilibrium expression are all the same. So we can simply raise the original KEQ to the power of that new coefficient. So we would take the original KEQ and raise it to the power of that new multiplier. Okay, let's practice. We have equilibrium, that's key, concentrations for the synthesis of ammonia. N2 is 8.5 times 10 to the negative 1, H2 3.1 times 10 to the negative 3, and ammonia 3.1 times 10 to the negative 2. First, we need to write a balanced equation for the reaction. 3 hydrogens, 1 nitrogen yields 2 ammonia. Next, we want to write the equilibrium expression. We're going to take products over reactants, and we're going to use the exponents from the coefficients of a balanced chemical equation. And then what we're going to do is simply plug in our concentrations at equilibrium, and we're going to solve for the value of K. (3.8 times 10 to the fourth). And what we're going to learn later is that the value of this gives us a little bit of information about what's happening at equilibrium. If the reaction is reversed and the coefficients are doubled, solve for K. So let's call the first one K prime. We learned that if it is reversed, we're going to take the value of the equilibrium expression and take 1 divided by that. So when we do 1 divided by 3.8 times 10 to the fourth, we get 2.6 times 10 to the negative 5. Now, coefficients are doubled. So we can go ahead and take this answer, K prime, and we can raise it to the power of 2, the multiplier. And what we find is our final equilibrium expression value is 6.9 times 10 to the negative 10. For a two-step reaction with K1 and K2, so if we have a multi-step mechanism, what we can find is that the overall, which we'll call K3, we can take each equilibrium expression, multiply them together in order to get the overall K3. The units for K will depend on the reaction. Each reaction may be different, and it takes into account non-ideal behavior, so we're actually not going to be using units. Let's talk a little bit about equilibrium position. Equilibrium position is a set of equilibrium concentrations. They depend on what you initially throw into a vessel. So let's look at 3 experiments. These are not in your notes. Let's see what happens. Initially, we have 3 different sets of initial concentrations. As time passes, we have 3 different equilibrium values for the concentrations. If we solve each of these for K, what we find is that K is unchanged. What may change the value of K is the change in temperature. So what does K mean? We solve for K, we get a number, but what does that number actually mean? A value of K that's greater than 1 means that equilibrium is far to the right, so mostly products have been formed. A value of K that's less than 1 means that equilibrium is far to the left, which means we have mostly reactants at equilibrium. The size of K and the time needed to reach equilibrium are not directly related. K values cannot always be directly compared because stoichiometry may be different. Last section here, we are going to talk about how equilibrium expressions can involve pressures and also heterogeneous equilibria, which we talked about earlier, containing a gas and perhaps an aqueous solution. We can write an equilibrium expression that involves pressure, and you'll note that in this equation, we don't just have total pressure, we have partial pressures here of each gas. Pressures can be used in equilibrium expressions. We call this, though, Kp. Using the same mass action equation above, you'll see the equation looks the same, but instead we're using partial pressures at equilibrium, and generally those are going to be in ATMs. There's an equation that relates the value of Kp with the value of Kc, but because gases are involved, we have to use gas constants. So in this equation, Kp is the equilibrium expression for pressure, equals to Kc, which is the equilibrium concentration. And then R, we're going to go back because we're using atmospheres for pressure. We're going to use 0.08, and you can use 206 if you'd like, liters, atmospheres over moles in Kelvin. So make sure your temperature is in Kelvin and your substance is in moles. RT is raised to the power of N, and it's delta N, which means it's a change in the number of moles of gaseous reactants. So how do we get this change? We're going to look at the balanced chemical equation, and we would be doing products, moles of products, minus the moles of reactants of gas. Kp and Kc can be interconverted using this relationship. Sometimes Kc and Kp can be equal if and only if the number of moles of gaseous product is equivalent to the moles of gaseous reactant. In that case, the change in N would be 0, and anything to the 0 power goes to 1. So let's consider a reaction at equilibrium of NaCl with NO and Cl2. It's at a certain temperature when 3 moles of NaCl and 1 mole of NO and 2 moles of Cl2 are mixed in a 10-liter flask. After the system has reached equilibrium, we're assuming that this is a closed vessel. The equilibrium concentrations are considered here. So these are all at equilibrium. Note that these are not the initial concentrations. Calculate the value of K for this system at 35 degrees Celsius. First thing I have to do is actually write out an equilibrium expression. Then I'm going to plug in equilibrium concentrations that were given above. When I solve for the value of K, EQ, or what we call Kc, 1.55 times 10 to the negative fifth. Part B, calculate the value of K for the reaction. And what you'll notice for NO plus Cl2 yields NoCl, it is the reverse equation. So using information previously covered in this video, what we can do is take the inverse of Kc, which we can call K prime in this case. 1 divided by the equilibrium constant will give us a value of 6.45 times 10 to the fourth. Part C, calculate the value of K for this reaction. And what we notice is that this is doubled the original concentrations for the original equation. So let's call this K double prime once again. If it's doubled, we will raise everything to the power of that multiplier. So 1.55 times 10 to the negative fifth squared gives us a value of 2.40 times 10 to the negative 10. And last but not least, applying our newest equation that relates pressure and concentration, we're going to calculate Kp for the first reaction. We're going to use the equation that relates the two. I am using the original Kc value of 1.55 times 10 to the negative fifth. I am using R 0.0821. Temperature was 35, but I need to convert to Kelvin, adding 273. And then I'm going to raise it to the power of 1. Well, again, where did that come from? We've got 3 moles of product, and we have 2 moles of reactant. Remember that this has to be for gases only. When we solve, we get 3.92 times 10 to the negative fourth.